This video provides an overview of sample size considerations, or how to maximize the power of a test. Whenever we test a hypothesis, we run the risk of making a mistake, because we make these decisions about populations based on sample data, and samples fluctuate. Whenever we reject the null hypothesis, we risk making a type 1 error, saying there's a difference when there isn't one. Whenever we fail to reject it, we risk making a type 2 error, failing to find real differences. We can only make a type 1 error if we reject the null hypothesis, and we can only make a type 2 error if we fail to reject it. This topic concerns minimizing type 2 or beta errors. The power of a test is its ability to find real differences. A power analysis is a method of determining the minimum sample size necessary to find a real difference if it exists. A researcher does a lot of preliminary work before doing a study. This work provides sufficient background to convince her that there is a real effect, and the study is designed to find that effect. Therefore, if the null hypothesis is not rejected, something went wrong. Perhaps the theory is incorrect, or maybe the pilot data were somehow faulty. Other factors that contribute to negative results are a poor research design, bad measurements, using the wrong statistical procedure, or inadequate sample size. A power analysis will eliminate sample size from this list of possible shortcomings. I'm going to use the independent t-test as a model for demonstration purposes, but the concepts are the same regardless of the test used. The goal is to set the power as large as possible given practical limitations. And I'll go through the 4 factors that affect power. We've looked at models of the null hypothesis, so this should look familiar. All possible values of the test statistic are shown on the x-axis. By setting the significance level, we determine both the critical value of the test statistic and the rejection region. It's possible to reject the null hypothesis when it's true, but we minimize this risk of false positives by setting alpha very low. The power of a test is a probability or area under the model of the research hypothesis, so we are going to focus on this distribution. Here, we're hypothesizing that the mean difference is greater than 0. If the research hypothesis is true, but our results do not lead us to this decision, then we've made a type 2 error, a false negative. This risk is equal to the area of this distribution to the left of the critical value of the test statistic, which we call beta. The area to the right is the power of the test. Any value in this region on the right will lead to rejection of the null hypothesis, which is the correct decision when the research hypothesis is true. This is a very busy diagram, so I'm going to simplify. This is the model of the null hypothesis, with a significance level of 0.05. When the null hypothesis is true, values of the test statistic to the left of the critical value lead to the correct decision, and values to the right lead to a type 1 error. Here's the model of the research hypothesis. This actually falls on the same x-axis. I've separated the models vertically so you can see them better. The red line connects the 2 models at the critical value of the test statistic. When the research hypothesis is true, values to the left of the critical value lead to a type 2 error, and values to the right lead to the correct decision. In order to do a power analysis, we need to place the research hypothesis at a specific point, so we need to specify exact values. I'm going to play with these models to show you the 4 characteristics that affect power and how they do so. First, let's look at the effect size. This is a measure of how different the research hypothesis is from the null hypothesis. This is what happens when the hypothesized mean difference increases, in this case from 3 to 12. The distribution shifts to the right and is now completely within the rejection region. So the power of the test has increased. Bigger effects are easier to see and result in more power. The significance level also influences the power of a test. Increasing alpha from 0.05 to 0.10 changes the critical value of the test statistic, thereby increasing the power of the test. This additional power is the area shown here in the blue box. We have more power if we are willing to take a greater risk of making a type 1 error. Sample size is the third factor that influences the power of a test. As sample size increases, the standard error decreases. So without changing anything else, the two distributions are further apart with a larger sample size because there is less variability in the distributions. Larger samples mean more power. The last factor that affects power is whether we are doing a one-tailed or two-tailed test. The rejection region for a two-tailed test is split into both tails, so that the area in the upper tail is less than it was for the one-tailed test. This means that there is less power with a two-tailed test, as depicted by the blue hash lines, than with a one-tailed test. A power analysis is usually done to determine the minimum sample size needed for a study. That is, we solve for n. If we assume that the research hypothesis is true, then we want to make sure our sample size is large enough to reject the null hypothesis. The three major factors to consider are the critical effect size, power, and significance level. Once these are set, we can determine the sample size needed. The critical effect size is the minimum difference needed to be considered important to society. For an independent t-test, this is the difference between the two means in standard deviation units. This is not a statistical consideration, but a clinical or practical one. Greenstein presents a clear discussion of this in the Topic 9 folder. The critical effect size essentially specifies the model for the research hypothesis. Here are other definitions of critical effect size. They all relate to practical considerations and have nothing to do with statistics. Specifying the critical effect size is one of the biggest challenges in power analysis. If you have some idea of expected variability, you can use this information. Otherwise, there are conventions that can be used based on small, medium, or large effects. These are in standard deviation units, so a medium effect size represents a difference between means of half a standard deviation. The second question is, how much power should you aim for? Generally, the answer is as much as possible. However, the minimum acceptable value is 0.8, or an 80% chance of seeing real differences if they exist. The significance level is important because we still need to protect against type 1 errors. We generally use a significance level of 0.05, but we would likely set a more conservative value if there are major risks associated with making a type 1 error, or might relax it if doing exploratory research. To summarize, a power analysis is done to determine the minimum sample size needed to find a real effect or difference if it exists. The four factors to consider are critical effect size, power, significance level, and whether the test is one-tailed or two-tailed. In the next video, we'll look at an example power analysis.